We are continuing our discussion about propositional calculus and logic. And what we had started off in our last lecture was an interesting domain of this logic or propositional calculus called the predicate logic. Okay, so let's just quickly revisit what was predicate logic. What was, first of all, predicate itself? Okay, so when we talk about propositions, which we had been studying throughout the last week, what are propositions? Propositions were simply some declarative sentence which necessarily had the property of being unambiguously either true or false. Okay, it couldn't be something between or something shady, sometimes this, sometimes that. So something which is unambiguously either true or false is something which we call proposition, right? So we talked about propositions which are quite straightforward in their truth value, but then we said that these are not sufficient. A lot of times in our computer science problems, or in general when we deal with different kinds of problems, we encounter certain sentences which may not be exact propositions, but kind of they have the scope to become such. Okay, what I particularly mean is, suppose I give you a condition that suppose x is greater than 3. We straight off know that it's not a proposition because it depends on the value of x, right? But it's not as generic as I say that, say, my name is Ikra, right? So my name is Ikra, this is true, or I make some vague statement, right? Wherein I cannot actually differentiate whether it's true or false, right? But this kind of statements is something in between. It's not completely vague where there is no sense of giving a truth value, true or false. Neither it's something which is very sure where you have a fixed true or false, which is a proposition. But these kind of sentences are something wherein you have a scope of making them proposition by giving some value to the variables, right? Such kind of functions are known as predicates. Okay, and in particularly, if I just write it in predicate form, so I can keep x as the variable. So this condition of being greater than 3 is what I called as the predicate, or it's sometimes also known as the proportional function. Yeah, I can denote it suppose by p of x. So p of x is a proportional function or a predicate wherein p tells you what kind of action do you want to perform on the variable x. And depending on variable x, when you perform this action or the property on variable x, you will be getting a determined or an unambiguous truth value, which will be either true or false, right? Which is like putting some value of x, say 1, and then you get straight off can tell whether the statement is true or false, right? So we have proportional functions. And how do we make them propositions? One straight way to do that is by assigning them values, and then checking the condition, and that would give us a concrete truth value, either true or false, which is unambiguous, right? So after that, once we introduced ourselves to predicate logic, so all kind of logic and applications which deal with such predicates comes under the category of predicate logic. Then what we moved on to was an important part of predicate logic, which is known as quantification. Okay, and what was the prime purpose of for quantification? Anyone recalls? Why is quantification required? Yes, class. Why do we require quantification? Yes, Rahul. You change proportional function to a proposition. That's the other way. So one way I told you how to change proportional function to proposition is by assigning value to the variables, right? So quantification is again another way of changing proportional functions to propositions. And the quantifier which we had last time discussed and ended our lecture on was the universal quantifier, which is also denoted by this inverted A, which you write as for all x, say p of x. And what does it mean? It means that first you define some domain. Okay, so in domain, if a particular property p or particular condition that you are testing p holds for all the values of x, then that's called its universal quantification. Okay, so that's where we had ended last time. We'll continue our discussion about the alternate forms of universal quantifier. Then we'll see today another quantifier called an existential quantifier, and also a uniqueness quantifier. And then we'll do, as I had mentioned, we'll discuss the tutorial on solutions. Okay, so let us start with the universal quantification. Again, have a kind of a recap of it. Okay, so let's start. So if you recall, what do we mean by a universal quantifier? A universal quantifier of a proportional function p of x is the statement p of x for all values of x in the domain. Okay, and where this domain is super important. If you change domain, your p of x truth value will change. Okay, so how do we check it? We say that a particular statement is a universal quantification of any statement if all values of the given domain satisfy that proportional function, right? And in general, if a lot of times what we can do is we can state a counter example. Counter example is that example for which the given proportion function is false. Okay, and we had seen these examples in the last class. So one way, the way you can visualize universal quantifier is as a conjunction. Okay, so let's see how can we visualize universal quantifier as a conjunction. So if you consider, as we know, whenever we define a quantifier, we need to have a domain. So now if you consider some domain, okay, so you define some domain, and if all elements in the domain can be listed, okay, so suppose x1, x2 till xn are the elements in the domain that you are referring to. And now if you have to apply a universal quantifier, which is like suppose for all x, p of x should be true, you can visualize it exactly same as a conjunction operation. Okay, that is, this condition should hold for p of x1 and p of x2 and so on and so forth till p of xn. Okay, and we know why conjunction here, because we know when we say for all x, this should hold for all the values in the domain. Okay, so I'm not keeping it as or but as an and. That means if one of them is false, okay, what will be the resultant value? If even one of them is these proportional functions, when I put them the values x1, x2, if even one of them is false, what would be the end result? It will be false, right? We know that intersection, if you remember the truth table, whenever you have even one false, you are bound to get a false only, right? So that is why universal quantifier can also be seen as a conjunction. Okay, wherein if you take the conjunction of all the values in the domain, what you're going to get is the universal quantifier, right? And this comes from the fact that conjunction is true only if all of them, all the individual components are true, right? So this is another alternate way of looking at the universal quantifier, that is as a conjunction. Okay. Now let's try this simple example. What is the truth value of for all x p of x, where p of x is a statement that x square is less than 10. Okay. Try to do it using conjunction. So how can I write the conjunction for all x p of x as a, a series of conjunctions? Yes, class, how can I write it? Tell me in these terms. What are the values that I should take conjunction of? So your domain is positive integers not exceeding 4. Okay, good. P of 0, P of 1, P of 2, P of 3, and P of 4. Right? This is my alternate way of representing this conjunction. Right? Now, put on these values in this statement and tell me whether it's true or false and what is the final truth value of this quantification. You need to simply plug in the values, right? Remember, p of x is what? You put in the value of x in your predicate logic and see if it holds. Okay, so here we are have x square by 10. So you put in the value of 0. It is less than 10, so it's true. then you put in the value of 1 here and see if it's true or false, right? 1 is also less than 10, so it's also true. 2 square is also less than 10 because it's 4. 3 square is 9, which is also strictly less than n, which is true. But what about the last case? If you look at last case, it is 4 square, which is not less than 10, okay, and it's false, right? So we know that if any one of them is false, it's going to be a false, right? And that's what we expect. When we say a universal quantifier, it means the condition is going to be true only if it's true for all of them in the domain, right? And we can see that even if one is failing, then it's a false. The truth value returned is false, right? Is this clear? Is this example clear, class? Universal quantifier as conjunction and this example. Okay, great. So let us move to the next quantifier, which is your existential quantifier. Okay, so a lot of statements in mathematics or even in computer science require us that a given element, it would be sufficient to have a single element with certain property. Okay, you don't need to kind of prove it for all of them. Okay, it's like suppose I want to organize or I want a student I want to participate in some art exhibition. Okay, so I don't need to ask every entire class that all of you should be interested in art or something, right? Even if I get one candidate, that would be sufficient for me. So such situations wherein you don't need to search the entire domain for the required candidate, but even if there's one, it would be sufficient. Such kind of properties or statements are what are represented using existential quantification. Okay, so in general, what is existential quantification? We say there's an existential quantification of a statement if the proposition, once you apply the existential quantification, is true. Okay, if and only if p of x is true for at least one value. Okay, so at least one is your, sorry, the other way around. So at least one is your requirement. It can be two, it can be three, it can even be all. But there should be at least one element in the domain. And if that is true, your proposition is going to be true. Okay. So formally, existential quantification of P of X is a proposition such that there exists an element X in the domain such that P of X holds true. Okay, so even if there's one element in the domain which for which p of x is going to be true, so that is what is we call as its existential quantification. Okay, and it's represented like an inverted mirror image of E, right? And the way we read it is there exists. Okay, so there exists is the word which maps existential quantification into our normal day sentences. Okay, so what is existential quantification? It is that form of quantification wherein you require at least one element in the domain to satisfy that property. Okay, further, like we had in universal quantifier, same thing applies for existential quantifier. You need to have a domain. Okay, if your domain changes, then your truth value will change. Okay, so in general, any quantification you have, whether it's universal, whether it's existential, you are bound to have some domain. If there's no domain, your meaning will is going to change. Okay, so these are some of the words in which you can see existential quantifiers, like there exists, or sometimes there is an x such that p of x holds, or there is at least one, or for some x. So these are the kind of key phrases that are used with existential quantifier. There exists, or there is at least one, or for some value x. Okay, so this is how you can identify existential quantifiers. Now let us see some examples. So suppose p of x is a statement x is greater than 3. What is the truth value of quantification? There exists a x such that p of x holds when the domain is real numbers. Okay, remember, existential quantifier is true if there is at least a one element. Even if there is one element, then it's fine for you. Okay, whereas in universal, every element had to satisfy the property. Okay, now what do you think is the truth value of this quantification? if your domain is the real numbers. Excellent. It is true. Why? Because we require just one case for which it is true, right? So just take case of 4 or anything greater than that, it's all true, right? So in existential, that's what you require. Even if there's one element which holds, for which this property holds, it is going to be true. Okay. Similarly, let us see this one. Let q of x be the statement x equal to x plus 1. What is the truth value of the quantification when the domain is again the real numbers? Yes, class? Is this true? Is this false? Is there any number which satisfies this? Okay, good. I want others also to attempt. It's not that difficult to see. Okay, so what we require one. Even if there's one element which satisfies this, then it would be true, right? But this is not true because there does not exist any real number which satisfies this property, right? But suppose I do it like this, then what would your answer change? X is strictly greater than x plus 1. Would your answer change? Yes, class, would your answer change or is it still false? It is still false, right? Because no number is greater than its successor, right? But if I do it like this, then what can you say about that? It is true, right? Because it's actually even, you can say it's true even for universal quantifier, right? Because every number is smaller than its immediate successor, right? So in general, so this is what you have. For when you have for all x p of x, you have to see all x in that domain should satisfy it. If all of them satisfy, then it's true. If even one of them fails, okay, if there's even one failure, then your truth value is false. Okay, and for there exists, the vice versa is true. You again look for x in domain, and even if there is one which is true, then you say it's true, and otherwise, for falsity, you need to check the entire domain. It should be false for everyone, only then it is kind of false. Okay, now can you tell me any possible way by which I can represent it in form of some operations like conjunction or disjunction, just based on the logic of how existential quantifier works? Like we saw, universal quantification can be written using conjunctions, right? How can we represent existential quantifier? Okay, you can see it from this statement. When is there exist p of x true? It is true even if one of them is true. Okay, if you have say three elements in domain, say p of x1, p of x2, and p of x3, even if one is true, it's going to be true. Okay, and when it's going to be false, when is the existential quantification statement going to be false? Yes, class? When is it going to be false? So that's correct, Shreya. I'm just trying to pull up everyone on this part. When is it going to be false? When all are false, right? So can you recall any truth table that you have seen which is true even if one of them is true, and which is false only the case when all are false, right? It is, of course, the disjunction, right? And that is what we have. Existential quantifier can be written as a disjunction. Okay, so if you have elements in domain, say x1 till xn, the existential quantifier is same as disjunction of the proportional function applied to these domains. Okay, so we know that with a disjunction, even if one of them is true, it's going to be true, and to be false, you have to show that all are false, right? So let us see again the same example. X square is greater than 10. but in context of existential quantification. Okay, so what is the answer we should get? Yes, class. Is what is its truth value? First of all, let us write it as a disjunction. So domain is positive integers not exceeding 4. So it is P1 disjunction P2 disjunction P3 disjunction uh, P4. Okay. So is it true? Is it false? Yes, class. What about others? Is it true? Is it false? Okay. So let us see if any one of them is true, right? So x square x square is greater than 10, so 0 is certainly not greater than 10, so it's false. 1 is not greater than 10, this is also false. 4 is also not greater than 10, this is also false. 9 is also not greater than 10, so this is also false, right? But if you look at the last one, it's true, and because of being a disjunction, even one of them is true, the truth value is true, right? Okay, so these were the two basic quantifications which help you to change propositional function to proposition. Okay, and how does it do that? By using the definition of the quantifiers. If you have a universal quantifier that is for all x p of x, you need all x in the domain should satisfy that property or proposition. And if you have existential quantification, then even if there's one element that satisfies this property, then your existent quantification is true. Okay, so this is a kind of a summary that when each of them are true or false. So for all x p of x, that is our universal quantifier, how do you show that it's true? You show that it's true if p of x is true for every x in the domain. Okay, so showing true requires you to prove that p of x is true for every element in the domain. Okay, and if you have to show that it's false, you need to show just one counter example, and that would be sufficient. Okay, you just need to show there exists x for which it is false. Okay, we know since it's a conjunction, even if one is false, then it's all going to be false. Okay, and vice versa holds true for the existential quantifier. We show that it's true if there's a single element. Even if there's a single element for which it is true, then you show that it's true. The truth value of this quantification is true. Okay, but if you have to show it's false, then you have to show it's false for every value. Okay, so kind of what you do for true and false is kind of swapped in the two quantifier statements. Okay, is this clear, class? The existential and the universal quantification, their representations. Yes, class, is this clear? Okay, excellent. Okay, so coming back again, back and forth, relating it to our computer programming and computer science. So universal and existential quantifiers have a great role to play in our loops that we frequently use in our programming languages. Okay, so let us see how can we visualize or contextualize the quantifiers in terms of looping. Okay, so if you look at the problem of looping, when you are kind of doing some sort of search, that can be found as very similar to doing quantification. Okay, so let's see how. So suppose there are some n objects in your domain. Okay, and you have a variable x, and it can take values from these n objects in the domain. Okay, now if you have to determine whether for all x p of x is true, then what do you have to do in this case? Okay, I have n objects from 1 to n in my domain, and x is going to take values from this. Okay, now if I have to prove, or I have to perform this action wherein I want to determine whether for all x p of x is true or not. There's some condition for looping I need to check, and I need to check it for the entire domain. Okay, how can I check it in context of looping? And then where do I stop actually? Just think it purely in terms of programming language. What should be my looping condition? What should be my looping variable? कहाँ तक मुझे loop चलाना है, and where do I stop? What is my stopping condition to, which is sufficient to show that for all x p of x is true? Yes, class. Anyone? You can just unmute yourself if it's difficult to type in. Come on, guys. It's already some hints are on screen, but I want you to try on your own also. Yes, class. How would you show something is true? Like for all x, p of x is true. We know how do you show it true? It needs to be shown true for all x in the domain, right? So if I have to do kind of looping, what should be my looping strategy? Come on, class. Is there no one who wants to attempt it? Great. So that's perfect condition to do. Very good. Okay, so that's what I had mentioned here as well. So you said in context of do while. So what you need to do for all x p of x is, since you want to check that every value in the domain is true, right? So that means you need to actually solve this p of 1, p of 2, so on and so forth, right? So basically you need to loop through all n variables from 1 to n, right? But when do you stop? As soon as you see even one of them failing, we know that even if one of them fails, then there's no purpose in looping. So like if I have 1 to n objects and just at the third object it fails, is there any purpose of looping over 4 to n in this case, universal quantification? No, certainly not, because even if I get a one false case, it's going to be false. So there's no need of wasting your efforts and resources. Okay, so that's where we can keep the stopping condition, that even if one is false, then you just stop and just return a false. Okay, but if there is no false, then actually you are going to loop till the end and return a true. Right? Now, what about the existential quantifier? What should be the stopping condition in that case? Okay, so for that, let's just quickly recall what was existential quantifier. You require one x such that the p of x is true, right? So what should be your stopping condition? How are you going to loop in this case? Lastly, this is important. I've been telling you from day one. Discrete maths is good for you only when you see related to your field. You know, that's very important, and that's where most textbooks or courses fail. They don't connect it. So you need to contextualize it. Yes, anyone? Sorry, Aditya, can you repeat? So what could be a stopping condition in this case? That's true. We have to still loop through n variables. Yes. So basically, what you can do is, like here you were looking for a false. Here you can be looking for a true, right? So if I have say x from 1 to n, and even if I get suppose true at the first shot, do I need to loop over the remaining for existential quantification? Do I need to loop over others, or even one is sufficient? You don't need. Remember, existential quantifier is there is an x for which p of x true. So even if you got the true value at the first shot when you tried for first variable, then there's no need to loop further, right? Only if you don't keep on finding any truth value and you hit the end, then you return a false, because there is no such value for which the p of x is true. Okay, So if you look at the universal and existential quantifiers in context of loops, the universal quantifier is like you are looking for a false statement. That's your stopping condition. As soon as you hit, you loop over all the values in the domain. But an efficient way to do it is don't go till the end every time. As soon as you hit a false value, you stop. Okay, and similarly for existential quantifier, what is the stopping condition? Again, you loop over all variables, but as soon as you hit a true, you stop. Right. So this is the context of universal and existential quantifiers in terms of looping, when you're kind of doing some search. Okay, is this clear, the two cases? Any questions, class? Please say a yes or no. I didn't get very good response in this part from you, so I just want to make sure it's clear. Is this clear to everyone? Yes, class, please type in, speak up. Okay, great. Okay, now let us move to another special quantifier that it's not very popular, because using universal and existential quantifiers, you can actually get back to this one. Okay, but in some textbooks it's referred to differently. So I just thought to discuss. So universal and existential quantifiers are like the most important quantifiers, because they can represent all sorts of quantification you want in any domain, whether it's mathematics, computer science, everything, right? But as such, there is no limitation on quantifiers. Okay, you can define your special quantifiers. Like suppose there are exactly two. This is also a quantifier. So in this case, what would you require? If I say there's a quantification, which is there are exactly two. Okay, so in this case, to prove that this is true, what would you require based on your understanding of existential and universal quantifiers? When would this be true? If I have this quantifier, there are exactly two. Yes, class. See, this is where I want you to build. We give you the inputs, and you should be able to generalize it. So we saw that in existential there exists at least one, right? So to show that this was true, I required at least one to be true, and it would be true. Similarly, for all xv universal quantifier, I required all to be true. Okay. So now if I define this special kind of quantifier which says there are exactly two, right? So when would that be true? Exactly. When if I have, suppose, I'm trying to look for values in the domain, exactly two of them should be true. Okay. If one is true, then would it be false or it would be true? If just one is true. If I use this quantifier, there are exactly two. Okay, it would be false, right? And what about if there are three or more? Would it be true or false? It would still be false, right? Because it's strictly saying exactly two, right? Similarly, if I have, suppose, this quantifier, there are no more than three, right? So what are the values of how many values of x are such that they should hold, so that this quantifier holds? Exactly, it's at most three. That means one, none, one, two, or three, but not four or five or so on, right? So what I actually want to highlight from this is universal and existential are like two extremes of quantification, but there's no restriction. You can define your own quantifiers based on what you're understanding, right? So whenever there's kind of at least, you're going to go for you're going to go for say or, and for all you're going to go for intersection, right? But the conditions may vary. Sometimes exactly two, sometimes more at most three, at least three. So they may vary. So there's no restriction as such. Okay. Now, what is this uniqueness quantifier then? The uniqueness quantifier is denoted by the existential quantifier along with an exclamatory mark. Okay, or sometimes existential quantifier, and then there's a subscript one. Okay, what does it mean basically? The uniqueness operator, denoted by this symbol, uh, actually states that there exists a unique x such that p of x is true. Okay, so by unique x, I mean uh, there should be only a unique value for which this is true, right? So it's not that at least one. It is there. It's talk about uniqueness. Okay, you cannot have more x for which p of x is true. Okay, like you can see in this example. So we have x minus 1 is equal to 0. Okay, and this domain is set of real numbers. Now, if we want to show that this is true, it's a special case of existential, wherein we have to show there exists a real number such that this is true, but that real number is unique. Okay, there are no more real numbers for which this is true. It's just a unique real number. Okay, and we know that this x minus 1 is equal to 0 is true when x equal to 1. Okay, so there is a unique number for which this is true. Is there any x for which this is true? Right? So that kind of special kind of quantification was like uniqueness quantification, wherein you are not looking at at least one, but it's like exactly one. If I put it in simple words, it is exactly one x such that p of x is true, and that exact one is your unique x. Okay, is this clear, class? Is this clear? Universal, existential, uniqueness, and different quantifiers. Sure, Tanya, I'll explain it again. Okay, so before I move to uniqueness, was this clear, Tanya, and to all others? When we talk about different variations, like there are exactly two or there are no more than three, is this part clear? Yes, Tanya, was this part clear or this part repeats repetition? Okay, so this part is clear. So I'll repeat the uniqueness part. Okay, so now before uniqueness, let's quickly again recall what was there exists x p of x. Okay, it meant there is at least one x for which p of x is true. Okay, so number of x's that for which this is true, it was at least one. Okay, so if I had the p of x is true for 1, 2, 3, anything, that is fine. As long as it's for 1, it's okay. Right? Now, what is uniqueness quantifier? Uniqueness quantifier, which is very similarly denoted as the existential with an exclamatory mark or with a subscript 1, says that this holds true if there is a unique x for which p of x is true. Okay, so you need a single, exactly one value for which this should be true, right? Like if I write x square is greater than 10 and the domain is like x is from say 1 to 4. Okay, or rather let me put it less than 10. So how many values of x from 1 to 4 satisfy this property, Tanya? X square is less than 10 and my domain is 1 to 4, right? How many values satisfy this property? 3. Very good. It is 1, 2 and 3, right? So this is not a uniqueness quantifier. If I do a uniqueness quantifier of this statement, it's false, because for uniqueness, what do you require? Only one should hold this property. Exactly one value of x should hold this property, and that exact value should be unique. Okay, so like if I kind of flip it, then is the existent uniqueness property of p of x true or false? Again, domain is 1 to 4. Excellent. Okay, so you got the point. So you can see if I look at this condition, x square is greater than 10, we know it fails for 1, it fails for 2, it fails for 3, but it's only true for 4. So if when your variable x, which satisfies this proportional function, is true, it's a unique variable. That in such cases, the uniqueness quantifier is returns a true. Okay, is that clear, Tanya? This is clear. This is clear to everyone. Okay, great. I'll stop there. As I said, I'll be discussing now the tutorial.